Ah. Hmm. So look at that. So things seems to move well. So I'm already online. Oh, God damn it. I made a mistake here. So I need to edit this because this is election number 6, not 5. Go live. Great. So the mic is on. Mic is on, and I'm gonna take myself to this YouTube channel to see how things look like. Live in my channel. There was some kind of a confusion because live in.
Can you increase the volume somehow?
So is it not strong enough?
No, it's good.
It's good. Okay, what about me? So do I look strong?
Yes, as always.
Do I look pretty?
You're not looking pretty. You're an engineer.
Do I look like an engineer?
Yes, you do.
Okay, very good. I'm happy. I'm happy.
Okay, just for the flex, because I just
Yeah,
looked.
this is. I see that this looks very good. Really, really good. And the screen is fantastic. Okay, I'm gonna take this volume off. See, we might even close a little earlier today.
Okay.
We might, depending how it goes, because we need to leave some stuff like summary for next week too. Yeah.
Okay. Okay. So where do you think that you will finish? Like, will you go to the end to that slider crank mechanism example?
I probably not. I think I
Because
might
that
leave
one
this.
is gonna take
Yeah, because I
super long.
might think I might leave these examples for next week. So we just cover these theoretical parts and then
Both examples?
no, one example, just the one. This
The last one.
simple one, and then the next one we can do this a little later. Yeah. Okay. Good. So do we have a meeting tomorrow? Yes, we do.
Yes, we do.
We
At
do. At
11:15.
11:15.
Yes.
Great. Sounds good.
And everything is going good.
Yep. Everything is going well.
Yes.
I'm gonna go in the Lahti region. Me too. Yeah. Gonna go to Lahti region.
Biology or for something else?
No, Lahti. I mean, city of Lahti.
Okay,
I'm gonna
that's.
be there on Wednesday.
I'm gonna discuss it further in detail, but somehow I realized that that person, I'm not gonna name her,
Yeah, because
yes,
recording is
yes,
already on.
and she's super interested to have collaboration, and we help
Okay.
him to do research.
Ah, okay. So that's a deal.
Yeah.
Yeah, let's discuss details tomorrow.
Okay.
Great. Thank you, Mustafa.
Okay. Should I go or should I wait till you
No,
finish?
no, you can go. You can go.
Okay, and try to follow that and see when you finish.
Yeah,
Okay.
yeah. Because it's been a long day today. I'm kind of like honestly, I'm a little bit beaten already. Seriously. I mean,
I know
I
the
feel I
reason.
feel only like super
I
strong.
know the reason. You know,
These,
when you switch to something lighter.
yeah, yeah, that may be the case. Could be the case. Can you see how many participants we have online?
18,
Eight. What the heck? This
and one is
is
me.
and
So
one is
sad.
me.
Yes.
This is really, really bad. How come we have? Because I see that there's less people here than usually,
I don't know, maybe there's some kind of.
like a party.
Yes.
Why is that I don't see in a picture? Is it? No, no, it's okay. It looks okay.
Okay.
It looks okay. A little bit here. I don't know if you noticed, but I edited the videos. So now every time we're getting started here, respect, you know. So I took everything, this hassle in the beginning, I took it away.
Ah,
Yeah,
okay.
yeah,
You're becoming a profession, like in terms of
yeah, I guess.
YouTube.
Okay, so it's gonna be in 15 seconds, and then they're gonna go.
I believe now is the time for you to giving up the professor life of becoming a YouTube star.
Yeah, that's what I say. I wanted them to call me like an influencer. That's what I am. Okay, okay, guys. Okay, guys, have you seen this? Have you seen this before? Respect. I'm worried. Guess why I'm worried? Because I see that there's less people in the lecture room than usually, a little less. But then what really makes me worried is that I checked from the YouTube that 18 participants only. 18. Not good. Not good. Because remember what I mentioned that what you need to do every single week is to follow the lectures. There will be no other way to survive. No other way. Okay, I said that it's going to be a, something that you're never going to forget when you're going to learn to do the first kinematic analysis. Today, much bigger thing will happen, way much bigger. Today, what we're going to do, we're going to run the first dynamic analysis. That's really a big deal, really a big deal. So pre-prepare to go the really emotional because you're going to see something that you can't believe by yourself. It's going to be a mechanism that we're going to solve the dynamic responses. And it's going to be great. It's going to be a big moment of your time in your lifetime. I think it may be the highlight of your life so far. So we'll see. So it's going to be a big time ahead of us. But then I have a little bit of bad news to you because I mentioned that what we do in this class, we're going all the way up to the summit of Mount Everest. We were in the summit of the Mount Everest. And those of you that are doing the mountaineering, I'm not the one of those, but I learned it and I watched the movies about the mountaineering. I learned that one of the things that is the most, comes with the highest possible risk is that when you're coming down from the summit. And now what we do today, we're coming down from the summit. And I need to give you a pre-warning, a little bit of heads up, because they're going to be avalanches. They're going to be broken ropes. They're going to be all this kind of stuff that we're going to face today. So it's not going to be pleasant, coming down, but it's going to be with multiple high-risk things. And one of the high-risk things is that we're going to discuss about the method, which is going to be based on Lagrange multipliers. How much you understood about this concept of virtual work, percentage-wise? Like 100% will be the full understanding, 5% will be not so much understanding. So which one were your understanding about the concept of virtual work? Like maybe closer to 5 than 100, I guess. Yeah, okay. Today we're going to discuss something that is even more complicated than that. So we're going to discuss about a little bit about the mathematics and how we can actually create the equation of motion. We kind of have to summarize everything we have discussed so far. But then, we almost can see the base camp and the helicopter waiting for us in a base camp. Because what's going to happen after this week? We're going to still cover the one more topic about the multi-body system dynamics, and then we're going to leave the entire topic about mechanical modeling. We're not going to touch that any longer, but what we're going to do afterwards is going to be how is that we can model the actuators. So we're going to take a look at the hydraulic actuators, completely different story. So no relation, no clear relation what we've been discussing earlier. Much easier because it's almost like 1 plus 1, how much is that? So it's much more simple than mechanical modeling. There's going to be other complications underway, but soon we're done with the mechanical modeling. But still one more thing to do is coming down from the summit. High risk journey. All right, so equation of motion, augmented formulation, and for your information this time already. So we can create the equation of motion in two different ways. We can either add our constraints to our equation of motion, or we can substitute our constraints inside of our equation of motion. Those are the two alternatives. The one that is based on Lagrange multipliers is the one that we're adding constraints to our equation of motion. Okay, that's what we're going to learn today. But first thing first, summary, what we did a week ago. So a week ago was one of those tough lectures. Well, maybe one of the hardest lectures so far in your life. Probably the most complicated lecture in your master degree studies. So we look at how is that we can express inertial forces in terms of generalized coordinates. Inertial forces is a mass multiplied by acceleration. But because we want to show off about our mathematical skills, instead of saying mass, we want to say, hey, we want to integrate the density over the volume of the body. And that's equal than the mass. But a bit more general way to say it. General because remember where we start with. We start with the particles. And now we can take the density of the particle into account. And we can take each of the particles into account by integrating over the volume of the body. That's what we did. Okay. Now the big task ahead of us was to express the force, this one that consists of two components. that are with respect to global x and global y with respect to generalized coordinates. And this transformation from 3, excuse me, to 2 to 3, we can make it happen with help of virtual work, virtual displacement to be more specific. Virtual displacement was this fantastic thing. We are assuming time not to run. And because time is not running and the displacement takes a place, not this planet. This is a mathematical tool for us. Don't think about it like how small is a virtual displacement and how it looked like in real life. Forget about all that. Think about it as a tool to do this conversion from one coordinate system to another. That's a better way to understand the concept of virtual work. Okay. Anyways, so what we did was that we introduced this is our inertial forces. We introduced this virtual displacement to make it as a work. So it's a force multiplied by displacement. This time virtual displacement. And the fantastic thing that happened to us when we do the virtual displacement, time is not running. And because the time is not running, we can relate global and generalized coordinates. How? With this magic matrix that you can get by differentiating your global position with respect to your generalized coordinates. That's how you can make it happen. Okay. Now, when substituting this stuff together, taking this concept of virtual work, this partial differentiation, expressing the acceleration as it is shown here, put this all in generalized inertial forces, something that came up with as a consequence of that was a mass matrix multiplied by acceleration of generalized coordinates and something that is called quadratic velocity vector. Okay, so 2 components. And not big surprise, because remember how was an acceleration? Acceleration, there was a components that were linearly related to acceleration and quadratic to velocities. So inertia must be related to these 2 different kinds of expression of acceleration. Okay, and that's exactly what happened. So we're going to have a mass matrix, and then we can have a quadratic velocity vector. And we learned something that simplifies our life in planar case. And something that simplifies our life in planar case was the fact that if we're going to set body reference coordinate system to center of the mass matrix turned out to be a diagonal matrix. If we're going to put the body reference coordinate system to center of the mass, we're going to have a diagonal representation of the mass matrix. If we're going to set the body reference coordinate system to be in the center of the mass, we're going to get the diagonal mass matrix. Yes. Guess what's going to come next? In-class quiz where I'm asking when you're going to get the diagonal representation of the mass matrix. You can get it when you're going to put your body reference coordinate system to center of the mass. But here's the thing, in a multi-body system dynamics, in a planar case, it makes a great simplification. Spatial case, not so much, because we need to deal with the rotations. And in a certain commercial codes, they actually, why they wanted to put their body reference coordinate system is completely outside of the boundaries of the body. And that happens too. It comes certain times, it gives you certain benefits in a computational procedures. But again, if you have a potato-shaped body like this, okay, and the center of the mass is located here. This is center of the mass. If you're going to put anywhere, you can put your body reference coordinate system anywhere you want, within the boundaries of the body or outside of the boundaries of the body. But you can get the great simplification if you set them to be, if you set your body reference coordinate system to be in the center of the body. And we're going back to where we start with. Remember what I said in the beginning, that if you guys going to score 100%, and I know, I still owe you coffee. I know, that's clear. And we can get back to these coffee serving practicalities later, this class. But I do know this, and I owe you big time. And I will make it sure that you're going to get your coffee. But I'm going to go back because I used my coffee kind of ticket already. So what if you're going to score 100%? This time, I'm going to call vector. Immediately. Immediately, I'm going to take a WhatsApp call to rector, like, look at me. And not look at me, look at you. Look at you guys. You guys are scoring 100% from this fantastically difficult question. And the rector will come and hug you, each of you, at the time. I don't know, probably not going to do that, but anyways, that's how it's going to go. Okay, then another thing we discussed a week ago, and this is the last slide about the summary. So we discussed about this quadratic velocity vector. So the quadratic velocity vector is like how much forces you need, how much forces you feel because of the body rotation. And if you have your body reference coordinate system in the center of the mass, you're rotating your body, you feel no translational forces whatsoever. No forces. But if it is in one end, yes, you feel these centrifugal forces. These are the ones that try to kind of break the revolute joint here. If there's a revolute joint like here, this is if I have a really high speed, they want to break this joint here. These are the ones that are representing quadratic velocity vectors. This is confusing because it's a force too. That is a force, even though the name implies that it's something else. But it's a force component, and it's going to be treated like forces because, again, because of the D'Ampère's principle. That's how it's going to go. Quadratic velocity vector will be equal to 0 if, and only if the center of the mass is located, if the body reference coordinate system is located in the center of the mass. So if you have a diagonal representation of the mass matrix, then the quadratic velocity vector will be 0. Okay. Now, let's take a look at this. First question, mass matrix of the body is diagonal if body reference coordinate system is located in the center of the mass. Body reference coordinate system is located outside of the center of the mass, but within the boundaries of the body. Body has a beam-like shape. Body reference coordinate system is located outside of the body because everything is possible. But one only is correct. Which one is correct? I have no comments on that. But then, you guys think about this. And Socrates is on. So please, let's take a look how many participants we have today. Gonna discard these changes made. Oh, you don't see this. Not this one either. Okay, so I feel bad. I feel okay again because I see that we have 100 answers already in a Socrates. 100 and why this is. Okay, you see this. We have 107 answers already. 107, and the number is increasing. 110. How was it a week ago? I think it was 120, 25, something like that. 135. Was it really that high? Oh my God, that's a lot. But I'm very proud of you guys that you make a commitment to follow the lecture every single week, because this is remember, what's the key to success? Following lectures every single week. No other way. All right, so we got 111 answers. So is it going to increasing or what? So it seems to left behind the number of participants comparing how was it a week ago. All right, so should I make Rector's phone number ready here? Okay, so you guys think that I should have him ready? Uh-huh. Okay, so let's first take a look at how we're doing the in-class quiz. Okay, 100% or not? Woo! Oh, oh. I don't know why I keep on playing with the fire. Sometimes, usually what happens when you play with the fire, you burn your face. Ooh. Ooh. I got scared when I see this red bar to go all the way to the right end. I was so sure that it's going to be 100%, but thanks God there's a friend of mine somewhere here in the class, good friend of mine, and say that the body reference coordinate system is located in outside of the body. Okay, I need to really stop doing this. But the next one is this one. Quadratic velocity vector is equal to 0. Okay, quadratic velocity vector, let me take back you this one here. So this is a squeeze, link class squeeze number 2. Number 2. And then we're going to move on to start to wrap up things. So we need to close the case about how we can create the equation of motion. Okay, so should I leave this and get back to this a little later? So how you guys want to go? Let's leave this and I'm going to revisit in this place after a while. Okay? So now quadratic velocity vector is 0 if body has a beam-like shape. Interesting. Body reference coordinate system is located in the center of the mass. Body reference coordinate system is located outside of the center of the mass, within the boundaries of the body. Body reference coordinate system is located outside of the body. Okay, these are the choices, and we're gonna leave this. We're gonna revisit in this place momentarily, but first we're gonna discuss something painful. Something painful will be this. Equations of motion. Okay. So what we know so far, so we know how is externally applied forces. We know what are the generalized inertial forces. So we know two different kind of forces. So we have this guy. So if you take yourself back, how was Newton's second law? You know, we have this externally applied generalized forces, and then we have inertial forces. We have them both. And we can express them both in terms of unknowns. And unknowns that we need to deal with are generalized coordinates. Great. This is really, really great. So we have all the components, but one is still missing. One is still missing because remember, something that we need to obey regardless of how big is a force is something that always we need to obey, not yet listed here. So we have external applied forces, inertial forces, but what else we need? We need constraints, because constraints are not yet mentioned here. So we need to take that into account one way or another. And this is exactly what I mentioned to you when I say we have two choices ahead of us. So we can either go left or right. If we're going to take a left, it means that we're going to add the constraints to this force equation with help of Lagrange multipliers. Or alternatively, we can substitute these constraints inside of the equation of motion. And that is called embedded formulation. Embedded, like embedding the constraints inside. Augmented, like adding them to the top of the what we already have. These are the two principal differences, and they are conceptually completely different things to deal with. And today we're going to learn what it means if we're going to add the constraints. But first, this is something we briefly discussed a week ago. We briefly discussed that what we really are interested in is that we want to collect all the work done by the system, not just a single body, but all the work done by the multi-body system. So now we want to take ourselves the one step above. We need to start looking not just a single body, but all the bodies. And what we can do for all the bodies is that we can actually add the work done by inertial forces, generalized inertial forces, and then the work done by generalized externally applied forces from each of the bodies in our system. So we kind of keep on adding them. So we take the body number 1 into account, we adding them all the way until we have the last body of the system accounted. And once we do that, then we can express the equation of motion, which is not yet the equation of motion, but let's say the force balance. Dynamic force balance like this. How much this is different that I just put it in writing in my previous slide here. No difference except that now the case down here, we have expressed the forces in terms of generalized coordinates. But other than that, there is absolutely no difference. We have here external applied forces expressed by using generalized coordinates and inertial forces. And inertial forces consist of two components. One where the mass is linearly related to acceleration and quadratic velocity vector. So this is our force balance equation. Great. Force balance. But still not all we need. But now this is already something that is extremely important for us because now we can build the mass matrix not for a single body, but for an entire multi-body system. I like also briefly mentioned a week ago, we're going to do this by using the technique that is based on this block diagonal representation. Block diagonal means that the first body, a mass matrix of the first body will be located here. In planar case, this is going to be 3 by 3. Second body is going to be here. And look what is important. Here, they do not overlap. They do not. And we already knew this because remember, if we have a one body, the vector of generalized coordinates consists of 3 components because every body needs 3 generalized coordinates. And if we have 2 bodies, then it's going to be 6. So we're adding them. We keep on adding them. This is exactly what we do for other components as well, including the mass and other components. So this is a mass. This is quadratic velocity vector for first body, which is a total of 3 components. Second body, a total of 3 components, so on and so forth. External applied forces, first 3 is for first body, then for second body, and so on and so forth. This is how we're building the system matrix for an entire case. One more thing that is missing here is this constraints. This is something that you guys are already familiar with. So you can make a vector from constraints such the way that each of the constraints that are independent constraint equations are accounted. Okay. Now other components like damping, we can deal with the same kind of the way, but let's just focus on the forces and constraints. Okay. Now, what we're going to do is that we're going to use this concept of virtual work. This is going to be big pain. This is going to hurt physically a lot to look what I'm about to explain to you. So be prepared to face the pain. Okay? So what I'm doing here is that I'm saying that virtual work done by all the bodies that are related to inertial forces, I'm going to set that to be equal than the virtual work of all the bodies that is done by external applied forces. Okay, I do this. And I'm moving everything to the left side of the equation. Then I have here my virtual displacement multiplied by generalized inertial forces, generalized external applied forces. And when I write this guy, the way that I learned to write it, this is it. Now, I mentioned a week ago that the concept of virtual work is often misused. And it's often misused because what is a very common scenario is that you think that you can take this part of the equation, and set that to be equal to 0. And that's not true. That's not true. This is the misuse of the concept of virtual work because it can be only set to be equal to 0 under certain conditions. And this is when things becomes to be complicated. And this is when you're going to feel this physical pain. I'm going to repeat this in a momentarily. This equation here, which is a virtual displacement multiplied by these generalized forces. In general case, you cannot set this to be equal to 0. You cannot. What's the big problem? Why not? You cannot because, if you do the virtual displacement like it is shown here. Then you're going to introduce the virtual displacement regardless of the constraints. You don't care about the constraints. What happens when you do that? Then the constraints will actually do a certain amount of work. And this component is missing here, is not here. So you can only set this to be equal to 0 if this displacement is kinematically admissible, kinematically possible. So if you do it like, don't care about constraints, you made a major mistake. This is not the way you can find an equilibrium. No way. You have to set this in a way that you have to express this to be kinematically admissible, or alternatively, you can take the work done by reaction forces and constraints into account. You feel it? The pain. It hurts. It's here inside, it's here, and it hurts. It burns. It burns big time. It's like, oh, take the pain off to my body. And I will. I will do that. We'll do it. Let's make this, that's going to be okay. But everything that comes after a little bit of pain has a more value comparing something that comes with no effort at all. That's why if you pass this course, make sure you're going to get the good credits yourself. Make your life to be wild. Take like extra cup of coffee or something crazy like that. What do you think? Why not? But let's first pass this course. First we need to do that. Okay. Now, like I say, I have two different ways to force, because what I need to do is that I need to force this equation to be equal to 0. And these two ways are augmented formulation or embedded techniques. Okay, this is something that I need to explain to you in details. So I cannot set this equation to be 0 because, I need to take this work done by reaction forces into account. And I can get rid of that if I express my virtual displacement such that it's kinematically admissible, possible displacement. That's what it is. Okay, now here is my in-class quiz. Equation cannot be set to equal to 0 because something is missing. Because inertial forces are not accounted. Because externally applied forces are not accounted. Constraints are not accounted. Or no forces are accounted. Okay, now let me take myself back to the in-class quiz and let me take a look at how we do in the first in-class quiz. And then we continue the story. This one. Actually, honestly, I'm a little too scared to look at how we're doing here because I'm sensing something super bad here. Super bad would be 100%. And then because I made the promise already, then I need to call the rector this time of the day, and it's past 4 o'clock, so he may be angry to me. Ooh! Oh, thank you. So I don't need to call the rector. So good news is this. So we scored really high in the quadratic velocity vector, but I think we got some latecomers, that the people that came late, that they were not aware of the correct answer, and the percentage came down. So I feel more relieved. Okay, so this was a question about the quadratic velocity vector. Second one is why this equation cannot be set to be equal to 0, because something is not accounted. What is it that is not accounted? Let me see the number of answers. 27, 20, 34, 34, 60 something, 70 something. Okay, so we are getting back to this after explaining something a little different first. Let me take you back to the mathematical class, okay? Because otherwise, sorry, I made this incorrect order. So let me take you back to the mathematics, because I'm sure you remember how to take constraints into account. This has been explained to you like a million different times in different kind of mathematical classes. I'm sure you remember that there are two ways: substitution or the method based on Lagrange multipliers. I'm sure you have heard this number of times before. So let me take yourself back to the mathematics. I have here mathematical assignment. I want to minimize the equation where the q is equal to 1 divided by 2 y1 power 2 y2 power 2. This is my function. I wanted to minimize the function in a way that the constraint that is also function of y1 and y2 is accounted. So this is a minimization problem with constraints, something that there's a lot of mathematics behind. You know how to solve this. What you can do is that you can take y1 or y2 and substitute that to your original equation like that, and then set this to be, differentiate this with respect to variables that is left, take a tangent from the variable with respect to variable, and set that to be equal to 0. That's the way you can minimize it, by taking the constraints into account. This is the simple procedure that I'm sure that each of you have heard before. Okay? Clear? So you know the strategy. You do the substitution, and then this is going to be, once you substitute this one here, then the only variable left will be y2. Then you differentiate this with respect to y2 to make sure that you can find where is the maximum and the minimum. And then this is how you can solve the y2 component in this particular location. You redo the same, but treating the second variable left. Okay, so here it is. So I got y1. So I do exactly like this. So I'm going to take this y2 here. This is going to go to another side of the equation. And then that is substituted here. Okay? No trick, mate. So this is what you're going to get. So you get this y, it gives me 1 divided by 2. And then parentheses, y2 power 2, y1 minus 1 power 2. This is it. Now, once you differentiate this with respect to y1, the only coordinate you have left, this is what you're going to get. Once you're solving the y1 from this one, it's going to be 1 divided by 2. The one left, which is a y2, you redo the whole thing, you do the substitution. So you first do this substitution, then you do the differentiation. Once you differentiate, you're going to get the y2 is going to be minus 1 divided by 2. This is what you knew already. You probably heard about another technique too. And another technique goes like this. It's a very straightforward, but it's a little of thinking needed, because this is how it mathematically look like. Mathematically the situation is as such. You have here a function, like this function that is described like this mathematical orienteering map. And then you have the constraints. You need to find the max of this map in such the way that you have to be within this path. You have to be within this curve. And this is where you need to minimize. This is where you need to find the minimum. Okay? So what you can do is that you can compute the derivative of these contour curves, and it will be here, but that's not going to be the one that you're looking for, because you need to find the highest point of the trail. And the trail is the one that is here. So what you can do is that you can keep on computing when is a delta of the trail and delta of the hill itself. And when those places are in the same line, that's where you get the highest point of your trail. That's where it is located at. Problem is that probably these deltas having a little bit of different length. So one of the deltas need to be multiplied by a random number to make them to be equalized. And this random number is going to be called Lagrange multipliers. So mathematically, you can find the highest point of the trail in this off-road environment by taking the delta or the function itself and the delta of the constraint equations and multiply one, this time constraint equation, with something that is called Lagrange multipliers. Let's use this concept and solve this problem we looked in the previous slide and see if we can find the same solution by using this technique based on substitution. Because I need to see if you're still alive. Are you still this? You can still manage? It's okay? How big is a pain? In a scale of 1 to, what they in the medical doctors, they're asking like, how big is a pain in a scale of 1 to 10? How big is a pain in a scale of 1 to 10? What, 11? What? How much? So it's like as big as it can be. Is it? No, okay, so it's that bad. Okay, that's okay. That's okay, because remember what I promised. I said that we were in the summit of the Mount Everest, and now we're coming down. Here's an avalanche. This is an avalanche, so we need to look at the avalanche. We may be surviving from the avalanche. Maybe not. It's unclear this time, but I'm sensing it's going to be fine. I'm sensing so. Okay, let's try to use this technique in the case of the previous example. And if we're able to do that, then that's going to be an alternative way to minimize the system. Okay, here it is. Here's the original function, exactly like it was expressed in a previous example. Now we're going to reformulate the constraints in a sense that the constraints will be set to be equal to 0. Remember, initially it was something that it was equal to 1. And now the 1 was put it in the left side of the equation. Okay, let's differentiate original function and constraints with respect to both variables that we have. What are the variables we have in this case? Okay, so let's call them as a generalized coordinates to make them to be close what we learned so far. So if we call vector of generalized coordinates, vector of unknowns, obviously this is unknown, y1. This is unknown too. What else? What do we have anything else here? No, that's it. That's all the variables we have to deal with. So obviously the vector of variables consists of two components. Now this is a scalar, this is a vector. So once we do the differentiation, such that this one here is a partial q partial y1. It's going to give us y1. This one here obviously is a partial q partial y2. It's going to give us y2. And then I'm going to do the same for constraint equations, that is the one located here. So first I differentiate constraint with respect to g with respect to y1. It's going to give us 1 because this one here. And then when I do that with respect to y2, it's going to give me minus 1. All right, so this is it. But one more thing was missing. Remember, it was such that, I have here this two vectors. These two vectors, I'm going to set them like this, and I'm going to put everything in the left side of the equation. So it's going to be like y1, y2, minus 1. This was a plus 1. And then this was multiplied by this. First need to be multiplied by this Lagrange multiplier. So it was a lambda minus lambda. Okay, this is unclear. So let me write this in a more clear way, because I wanted to say this one here. So it's y1, y2. And then in another side of the equation, I have here this lambda multiplied by 1 and minus 1. Okay, when I do this multiplication, it's going to be like this. So it's going to be minus lambda, and this is going to be plus lambda. And when I move everything in on the right side, left side of the equation, This is what I'm going to get. Problem is this. Now I have three variables because I added one more variable. I added one more unknown. I started with two unknowns, and now I add one more unknown. So it's just like I'm going in incorrect direction because what I did in the embedded technique, the substitution technique, I was reducing the number of unknowns. And now I'm adding the number of unknowns. Is it going to make our life to be unbearable? Something we cannot deal with this? No, this is something that is actually pretty pleasant too. Because even though that we have here mismatching number of unknowns and equations, we can get one more equation into account, and the one more equation is the constraint equations, as they are. Now we have a matching number of constraints, equations, and unknowns. So we added the unknown, and we added the one more information, that the information was the constraint equations. Okay, now when we solve this set of equations, we can get, first of all, we can get the y1 is equal to lambda, y2 is equal to lambda. But then when we're solving the lambda, lambda is going to be minus 1 divided by 2. And when we're using this information, we get exactly the same information. This needs to be repeated. So I'm going to go, here's what I'm proposing. Can we have a break? Short one. 5 minutes only. Is that okay? Like only 5 minutes. Can you live with that only 5 minutes? Okay? We're going to have a 5 minutes break, even though that is not yet 5 o'clock. 5 minutes break, and then I'm going to explain this again in terms of mechanics, because so far mathematics. But why don't we do this whole thing but using mechanics and see what we can learn from this. But this was a method based on Lagrange multipliers. And the Lagrange multipliers, we added the constraints original equation with help of Lagrange multipliers. That's what it is. And the Lagrange multipliers, they have a clear, not clear, but in mathematics, they said that is a price we have to pay because of the constraints. Price we have to pay because of the constraints. In mechanics, that is a clear. It is a reaction forces due to the constraints. That's what they are. Okay, so let's have a break, 5 minutes, and then we continue from this. Just the five. Just 5 minutes. You need more? 6. Okay, let's make it 6. They want to have a 10. Is it something that you need to go to cafeteria in 10 minutes or what? I just need to some time to recover, right? Okay. Well, let's have a 10 minutes then. 10 minutes. Okay. You guys ready? You're ready. Good. I checked the comments from the YouTube, and when I was asking like how big is a pain, like in a scale 1 to 10, well, I got the answer 10. Yeah. It's going to be even higher pain soon. But then we almost see the base cam, so we almost see it. So there's a little more pain, and then we're gonna be good. What do you guys say? And this is now the honest thing, so there will be no surprises here. Last time I wasn't completely honest when I said that this is it. So summit is, and it is like I said. So we went to all the way up to the summit, and now the coming down is when we face all these high risk things. Okay, okay. One more thing. So we solved this minimization problem by taking the original function, computing the deltas of the original function with respect to our variables. And we did the same for a constraint equation. And to make these two components to be equal in a length, we multiplied the one by with unknown variable lambda. And now we add the one more variable, we add the one more unknown to our system. And because of that, we need to increase the number of equations. And we did this by adding constraint equation to our set of equations. So that's what we got. And now this is something that we can generalize. So we had a simple example about one function, one constraint, but they could be, instead of one function, it could be a more complex multiple dimension problem, and the constraint could be consist of multiple components. And when we do that, we can express the same concept of Lagrange multipliers as it is shown here. So we have here delta f, which is original function, delta constraint equations that are multiplied by Lagrange multipliers, and then I have here vector of constraints. So this is when you generalize this in multiple dimensions. And this delta can be expressed in a way that is a partial function, original function, with respect to variables. Variables here are called as a generalized coordinates. And we can do the same for constraint equations. The constraint equation that are, we take a partial differentiation with respect to constraint equation. With respect to our variables, we get this delta Q. This is something we have met before. Actually, when you look at this partial differentiation, this is something that you kind of start sensing, okay, this is what you have met before. Because remember how we got the vector of generalized external applied forces and a vector of generalized inertial forces. We got them through the differentiation, partial differentiation. And this component, this original function, is actually our forces. It's inertial forces minus external applied forces equal to 0. That's what it is. Then this one here, which is a constraint equation differentiated with respect to variables, you have met this one too before. That's going to be Jacobian matrix. Because remember, Jacobian matrix is all about this partial differentiation from the original function with respect to your variables. Now, when you're adding this information, you can write your equation as it is shown here. So I have here first this original equation, and then something that is added to that. Now this one can be set to be equal to 0. Now finally we are able to force something to be equal to 0. And once we do that, then the equation of motion can be written like shown here. This is still not enough. Like in this example, remember we added the number of unknowns. Here we did the same. So we have the first original number of unknowns, which is this vector here, which is a vector of generalized coordinates. But then we added the more unknowns, and we added the Lagrange multipliers. The number of Lagrange multipliers is same that the number of constraint equations. Now, because of that, we need to get more additional information. And additional information we can get by taking constraint equations into account. That's the whole set of equation of motion. That's what it is. This is something that is called differential algebraic equation. And this could be the point where we stop the discussion. So we can solve this as it is here. But there's one more complication. And the one more complication is that if you look at the time integrations algorithm, time integration schemes available out there, most of them are made for ordinary differential equation, not this kind of the system which is a differential algebraic equation, but ordinary differential equation. So the last final step we can do is to convert this to be ordinary differential equation. And that's when I promise I'm stop torturing you. No torturing after this in this class. And that's my promise. I'm not going to say another cup of coffee if I violate against my promise, but I'll do my best to obey my promise. Okay? All right, so one more step to go is to convert this one here to be ordinary differential equation. And we can do this by differentiating the constraint twice with respect to time. This is something we learned when we were dealing with the kinematic analysis. And when we do that, we can have one more vector, which is called vector QC. And this is the one you can get by differentiating the constraint twice with respect to time. And now when you do that, then your equation of motion look like this. And this is where we're going to stop. So let me summarize. So we started here. We started here, but we were able to express the equation of motion like this with help of Lagrange multiplier. So we add the constraints to our original force balance equation. But this wasn't enough because this one here is unknown and this one is unknown. So we will have to create additional information to match the number of unknowns and equations. And the additional information we were able to get were constraint equations. We could have stopped there, but we wanted to take one more step ahead. We wanted to convert this set of differential algebraic equation to be ordinary differential equation. And we did this by taking this equation and differentiated that twice with respect to time. And we were able to land to this particular set of equation of motion. Okay, look what we have here. What is that we know about this? This guy here is a mass matrix. Good friend of ours, so we know him well. So this is something that is no surprises for us. What about this? Jacobian matrix. That's our middle name, so we know this back and forth. So it's no surprises, something something we are familiar with. And then comes, here is a Jacobian matrix with the transpose operation. This is an acceleration of generalized coordinates. We know that. This is a new friend of us, Lagrange multipliers, which is due to the constraints. And the physical interpretation is a price we have to pay because of the constraints. What kind of price we have to pay because of the constraints? Think about this kind of the pendulum here. Here is a revolute joint. Here is where the constraint is located at. What kind of price we have to pay because of this revolute joint? Reaction forces. The reaction forces are along the global x and y axes. That's what these Lagrange multipliers are representing. So they're representing the numerical values of these two force vectors. When you multiply them by Jacobian matrix actually telling me where these forces are located at in your system. Let's continue then. Then I have here vector of external applied forces. Good friend of us, so no surprises here. Quadratic velocity vector, a little bit of odd guy, but we know this before, so no surprises. And the last guy was the one that we just learned to deal with, the one we got when we differentiate the constraint twice with respect to time. Okay, now comes something surprising. The vector of unknowns is this vector. Okay, what is that we have here? What is that we have in this vector? We have here all the generalized coordinates. Okay, let's look at this pendulum example. What's going to be the number of generalized coordinates in a system like this? So it's a one moving body, and every body needs 3 generalized coordinates. So it's going to be 3. What else? We have Lagrange multipliers. We don't know them either, so those are unknowns. How many Lagrange multipliers? Same number than constraint equations. How many constraint equations we have here? 2. So it's going to be a total of 5 unknowns. 3 of them representing configuration of your system. 2 of them representing reaction forces due to the constraints. So 5 in total. 5. Clear? Okay. So now what if I have what about this? What's going to be the number of unknowns in case like this when I have a double pendulum? I'm sorry, this drawing is unclear, so let me make this another one. So there is a one beam-like body, another beam-like body. What's going to be the number of unknowns? Okay, let's vote. Number of unknowns will be 2, like a 2 degrees of freedom system. It's going to be like 6, 6 generalized coordinates. It's going to be 4, like 4 constraint equations, or 10, 10, or 100, because the bigger, the better. What's the correct answer? 10. How you guys came up with the 10? Because 2 bodies, each of them requires 3 generalized coordinates, 4 constraint equations. So it's going to be 6 plus 4. 6 plus 4, that's 10. Okay. You feel that, can you feel it already? So no, the pain is not bad anymore. It's still, you feel it, but it becomes to be a little less painful, right? Great. Okay. Now we're in a phase that we can actually start using the knowledge that we have gained so far. Like promised. What we're going to do is that we can apply this one here to practical cases. And believe me or not, you can solve any mechanical system using this set of equation of motion. How that's going to be possible? By following the certain steps. Remember what's not allowed in a multi-body system dynamics? Thinking. Not allowed. You just need to follow the certain procedures, no thinking whatsoever. You're going to get the equation of motion automatically. That's what's going to happen to you. So you're ready to practice. What we're going to do, we're going to practice, and then we're going to apply this to mechanism that's not very complicated, and then we're going to run this. We can analyze the system using the MATLAB. Ready for that? Okay. So let's go. The first question is, the arithmetic formula is that the unknowns are what? Okay, this is, I have still some unfinished businesses in in-class quizzes. So the unknowns are acceleration of generalized coordinates, Lagrange multipliers, generalized forces, acceleration of generalized coordinates, and Lagrange multipliers. One only is correct. Okay, let me take myself to Socrates, and let's take a look where we are. So you don't see this. Oh, not this one. Okay. How is the success rate of this one? This was the hard question about why this cannot be said to be equal to 0, because of inertial forces are not accounted. The external applied forces are not accounted. Inertial forces are here, so they are accounted. External applied forces are here, so they are accounted. Constraints are not accounted. Yeah, that's the correct one. And the, ooh, oh my God, this is really playing with the fire, because it's getting late. This late, and if they're If I need to call Rector at 6 o'clock, he's going to be mad. He's going to be unhappy. He's going to say, "Okay, why don't you meet me in my office tomorrow morning, 8 o'clock?" So thanks God you're playing with me. So we're obviously in the same team. Okay, good. But still, great success rate. Really good one. Okay, and then next one. In augmented formulation, unknowns are what? Acceleration of tenderized coordinates. One only, by the way, is correct answer. Lagrange multipliers, tenderized forces, acceleration of tenderized coordinates, excuse me, the acceleration of tenderized coordinates and Lagrange multipliers. Okay, so please enter your answer, and then we're gonna go back to this one. Okay, I need to do this trick one more time. Okay, so what I want to do here to demonstrate the skills we learned a little while ago was to solve the response, dynamic response of the mechanism shown here. So this is a simple planar system consisting of one moving body. Point P is constrained by a primitive joint that can slide along the global y-axis. Point Q is constrained by a primitive joint and it can slide along the global y-axis. And there is one body only in a system. Okay, so this is what I wanted to do. So I just need to follow the certain steps. Once I follow the steps, I have my equation of motion up and running. Good to go. Good to go to solve by using any, whatever numerical time integration scheme you wanted to solve that. Okay, but let's take a look at this one first. Oh, actually, we're not going to look at this one. But what we're going to do is one more in-class quiz. You said that there's a lot of in-class quizzes today. I have one more question to you. The question is this. In this example, the number of unknowns is 1, 2, 5, 99. 99. 99. Okay. Okay, but you are not able to answer that yet because there is some unfinished business here in my in-class quiz. This one. Okay, so I got 119 answers, 122 answers. This question. Okay, so I'm gonna close this one. Is it gonna be or is it not? Yes, it's not. 100%. Not 100%. This is gonna be absolutely the last week that I'm playing with this thing. My heart is not taking this well. It's a too high risk game. Too much to deal with. Okay, so we got 79% success rate, which is fantastic, really fantastic. And the next one, what's going to be the number of unknowns? Is it one? As a one body. One body makes sense. 1 degrees of freedom. 1 degrees of freedom makes sense. Two, like two constraints, makes sense. Makes sense. What is this 5? I don't know what this is 5 is. And then 99. I have to play like this. You understand this. You know the reason. Okay. Okay, and I'm going to leave this for a while. And then I'm going to start moving with the certain steps. I need to take this off one more time and put it back momentarily. Okay, like this. And this. Okay, now look what I'm doing here. Look what I'm doing here. I'm going to have these steps. And if you follow the steps like I do here, you're going to get the equation of motion automatically. Step number 1, create the mass matrix. So we learn how to do this. This is what we practiced a week ago. And again, highly recommended you to take a look at the pre-calculated tables. Don't try to use this overly sophisticated math because you can easily get confused about this It's complexity of the math. So don't do that, but instead use a pre-calculated tables. Okay, mass matrix consists of three components. First component is a 2 by 2 submatrix where the mass of the body is located in a diagonal component. And the mass is going to be given to you like this. So that's going to be the first part of the mass matrix. Second part of the mass matrix is going to be 0 because the body reference coordinate system is located in the center of the mass. So this guy going to be equal to 0. What is left is going to be mass moment of inertia. A mass moment of inertia, you can compute it nicely by using the math, or if you want to save your brains, which is recommended here, then you take a pre-calculated tables, and what you're going to get as a result is mass multiplied by length power 2 divided by 12. This is what you can find if you go to Google and you type mass moment of inertia table, and you're going to get the multiple different options how to get the different shapes of the bodies and the different ways where the body reference coordinate system is located at. Just select the one where the body reference coordinate system is located the way that you wanted that to be located at. Okay, so I'm ready to express my mass matrix. It's going to be a diagonal matrix. It consists of three components because of the one body only. And every body needs three tenorized coordinates. That's why the dimension of the system is 3 by 3. No additional bodies, so my full system mass matrix consists of 3 by 3 matrix. That's it. Done with the step number 1, and I'm going to move on. So I'm going to take a step number 2. Not easy one, because this time I need to compute my Jacobian. I first need to create the constraint equation, 2 of them. Then I need to differentiate my constraint equation with respect to my unknowns. My unknowns are tenorized coordinates, and every body needs 3 tenorized coordinates. So my Jacobian matrix will consist of 2 rows, 3 columns. That's going to give me the information about the number of degrees of freedom immediately. The number of degrees of freedom is going to be 1. Okay, all right. So let's make it happen. Let's first compute the constraint that is associated to point P. The point P that is going to be the one here, this one. So how you're going to make it happen? So you first need to get started here in origin of the global coordinate system. You need to move there where the origin of the body reference coordinate system is located at. And then from here, you need to move wherever the constraint is imposed. Okay? So you here on your x-axis of your body reference coordinate system pointing downwards. So you need to solve minus L divided by 2, and the y direction is 0. This is going to be your first constraint equation. You redo the same, but for this point here. Now you're going to go here, and here you're going to go here. So now this time your u bar x component is L divided by 2. You're going to get the second constraint equation. You differentiate that with respect to your variables. Variables are listed here. So it's Rx, Ry, and angle theta. Okay, you're going to get, as promised, you're going to get the matrix with 2 rows, 3 columns. 1 degrees of freedom system. Step number 3. Generalized external applied forces. This is going to be simple. That's not going to be too complicated because, look, I only have a gravity force applying in the system. A gravity force is applying in the center of the mass. That's the same location where the body reference coordinate system is located. All right? But let's make this in a proper way. Let's make this in a way that we're going to first express the point where the force is applying, this point. This point, the vector u bar is 0. Okay? So only thing left going to be this. When you differentiate that with respect to your variables, you will get easily this kind of mapping matrix where this is 1, 1, Rest are zeros. You multiply that with your force vector, you're going to get the three components. The one that is associated to angle theta is going to be 0. Step number 3, done. Look how simple is life. Oh my God. You know, it really pays off to commit yourself to educate and learn these kind of new things, because now everything is downhill. Sun is shining, no rainy days at all, so everything is beautiful. Because all the knowledge you have gained so far, it becomes to be useful. Okay? But it's getting better. This is not even the whole story. It's getting better all the time. Okay, the next one, quadratic velocity vector. Forget about it. We know that it's going to be 0. Why? Because the body reference coordinate system is located in the center of mass. 0. Step number 5. That's only, okay, not the rainy day, but the cloudy day. Let's say that this is a little bit of cloudy day. The cloudy day goes like this. We need to compute this a little bit of painful component. So we first take a Jacobian, multiply that by velocity of generalized coordinates. We're going to get the vector of two components. This vector will be differentiated with respect to generalized coordinates. It's going to give you the matrix where there's a 2-row, 3 columns. That eventually is multiplied by velocity, this one. This is eventually multiplied by velocity of generalized coordinates. This is what you're going to get. And this is the last step, step number 6, equation of motion. I'm just checking like for the information of online participants. So we have roughly, let's say 100 people in a class, and 99 out of the 100 are crying here in loud because of this is a big moment. So we have an equation of motion here. So we made this whole thing by ourselves. So we were able to do it. Great. Look what we have here. So this is what you need to invert. So this system matrix, this is your mass matrix, your Jacobian. Your Jacobian, that is with the transpose operation, this was matching the dimension, external applied forces, and this was a QC. Okay, maybe too much you to deal with, but let me ask this. Is this too much if I'm going to solve this by using MATLAB, or is it too much for one day? Because of this happy moment, we see the equation of motion. Would you like to see how is the response to it? Seriously? But it's going to be more crying. Let's take a look. Let's see. Where's my mouse? Discard. Okay, and you don't see this, so let me put this back to you. Okay, guys, here it is. So this is my MATLAB implementation. So I have here generalized coordinates. I have my position, velocity, level. I'm going to get back to this implementation next week, but I have my unknowns that are position and velocities. Because what I'm going to do is that I'm going to, do this integration in like pretty much like you're going to see in this implementation. I have here initial values. So I'm going to give you a value for the mass, gravity constant, length of the body, initial angle, and then the QC is going to be just predefined. This is going to be my initial position in global, Rx, R. This is going to be the velocity of Rx. This is going to be Ry, velocity Ry, theta, and theta dot. This is it. And then this is my mass matrix. And then I'm calling another vector, other file here, which is, which one is that? I'm looking, like this one here. Okay, there I have further information here. I have here my force vector. Oh, no, sorry. This is my Jacobian matrix. This is my force vector. This is where I do the assembly. And then I'm thinking that I'm ready to solve this system. So let's see. Is anything happening here? Yeah, it's coming. Ooh, this is a big moment. So let's see how it's going to be the visualization. So let's see where it's going to put these windows. So maybe we are now, where is it? So the same thing happened than the last time. So now it's again somewhere. How come I solved the thing last time? Because it was somehow hidden and then it appeared eventually. But how did I made it a week, couple of weeks back when we solved the kinematics? Because again, there are somewhere hidden here where they are. No, they're not here. Where is it they are? Hmm. Was it something that there's like I need to do this, I need to check this duplicate. So why this is not displaying it? What was the trick that I did a week ago? 2 weeks ago. Remember? Yeah, me neither. Okay, let me try to solve this one more time because I solved this during the break and then it was okay. Somehow it disappeared. No, same thing is somewhere hidden where I don't know where is it. Huh? Okay, let me do it there without this. I think is that the projector is a problem here somehow because when I was doing that by myself a while ago, it went okay. It was oh, is it overleaf? I mean the OBS that is somehow messing this up. Press any key to visualize. Huh? What a disappointment. Let me take this away. You don't see what I'm doing here, but I'm just explaining in loud that I'm. It's almost like you being in a dentist. So the doctor is explaining your stuff and you are not able to respond. Okay. Why? Major disappointment. No, I'm unable to display this to you. Just cannot. I just don't know where these windows are disappearing. They're obviously someplace else. So no. Let me put this back. Okay, so what I'm gonna figure it out this for next week, and then I'm gonna show this to you a week from now, and then week from now there is something that is extremely important because next week what we're gonna do is that we're gonna summarize everything we have learned so far. I'm gonna give you like a training for midterm exam. At the midterm exam, one more time, it's gonna be week 40, 40, what's it, 43? Okay, the week where the Monday is at 21st of October. That's when it's going to be held. And listen to me. So it's going to be in a Moodle. So only things you need is your big brains, your computer, and internet access. You can do it anywhere you want. So you don't need to be physically in university. You can go any place you want. You log yourself to the Moodle. I learned that the Moodle is not cooperating today, but hopefully it's cooperating in that particular week. You click that I'm ready to get started in my exam. But once you click that, then it's go. Then there's a question bank. So even if you think you can have your WhatsApp team and you can be a good buddy of our WhatsApp officer and asking which is the correct answer from WhatsApp officer, it's not going to help you because each of you going to get the individual questions from the question bank. There is going to be question. There's multiple choices, or you need to compute something. You need to answer that question similar way, exactly similar way you answer the questions in class. I mean, in weekly homework and in class quizzes. It's like combination of the two. Okay, you enter all your answers. You can modify your answers as many times you want. But once the 2 hours is done, then the answers are submitted to system, and then you're gonna get how many points you're gonna get. And if you're not happy with the points, you can redo your exam. The highest will be accounted. You will have two attempts. Two attempts. And that's what's going to happen. But I'm going to give you examples. What kind of the questions you expect to see? Highly recommended is that you do your first attempt on Monday, Tuesday latest. And then if you're not happy with your score, you keep on studying. You do your second attempt on during the weekend, Saturday, Sunday. You can do any time of the day you want, any day you want, two attempts, 2 hours max. And again, it's a question bank. So there's, even if you were sharing information with your fellow students, that's not going to help you much. Um, and then something that is confidential, but I'm going to share with you. So we have a highly educated artificial intelligence that is comparing your weekly assignments and your this midterm exam. If we suspect any wrongdoing, there's going to be awful destiny ahead of you, and that's going to be oral exam. Oh my God. Oral exam. If we suspect that there's something wrong, you're going to get an invitation. Why don't you come and have an oral exam? Many people, they had a heart attack immediately, so they're unable to meet us in oral exam because it's a, well, think about it when you see an email like this. It's an awful thing. Really, really unpleasant thing that can happen. But this kind of stuff can happen. Okay. But we get back to this training a week from now. A week from now, there's going to be one more example. This example that I'm gonna show you momentarily. I'm not going to show this to you today because I want to show the response to you in the MATLAB because that's going to be, as promised, it's going to change your life. You can, after that, you can say, was this before or after? And before or after means like before this class because it's such a big thing in your life. But one more thing before we go is make this in-class quiz. Okay, I don't think it's going to be 100%, so I'm kind of relaxed. This one here. Okay, so we got 132 answers, and what's going to be the number of unknowns? The correct answer is going to be, you don't see this. Correct answer is 199. No, that's not even an option here. Whew. I need to do something for this. I really need to do something because you guys obviously developed some kind of like a plot or something against me. I'm sensing that you're sharing on information which you're allowed to do. I recommend you to share the information. So even if you have the WhatsApp group, use it. Use it. Even if you have a, do you think that the ChatGPT can answer this correctly? This in-class quizzes we haven't tested. So it's hard to know if they can answer. They probably cannot because there's a picture and they don't read so well these pictures, so hard to tell. Okay, now I need to go home. So I want to close a little earlier than today, so it's going to be 5 minutes earlier than usually. So that's about it. And I'm going to make sure that the next week the MATLAB is going to be up and running and it's going to work well. And make sure that you're going to be here next week because it's one of the most important, if not the most important lecture. Yes, sir. Yeah, that's going to be the something that I'm going to say for next week. But I can tell you to you already. So it's going to be this one. You don't see this so well, but it's going to be what's the number of unknowns in this example? These are the options: 2, 6, 11, 14. No comments. No comments. Okay, guys, go home, relax, collect the energy, and come back next week. Oh, there's one more question. How many questions in a midterm? I'm going to get back to that next week. But again, make sure that once you do your weekly homework, keep these answers somewhere in your folder because it becomes to be handy, extremely handy. So you just take the new parameters, put it in your system, you get the correct answers like just like that. All right. Okay, guys, take it easy. See you on Monday, next week, Monday.